Okay, so we started talking about voltage regulation in the last class. And what we said was voltage regulation basically refers to what is the voltage drop that is happening within a transformer. And within a transformer, if you look at it, the series parameters are the resistance of the primary and secondary windings, that is R1 and R2. And when I refer R2 to the primary side, I write that as R2 dash. The same way, the leakage reactances are X1 for the primary winding and X2 dash, which is actually referred to the primary winding. It is the leakage reactance of the secondary winding referred to the primary side. So these four impedances or reactances, they are coming in series. Whereas if you look at what is RC, that is the core loss component of resistance, and the magnetizing reactance XM, both are going to be parallel parameters. And we said earlier itself that the current that is carried by the core loss component of resistance, we call that as IC, which is the core loss component of current. And this is going to be the magnetizing current, which is actually causing the flux to be established in the core. And because it's a ferromagnetic core, the reluctance is very, very minimal. So IM is going to be less than 5% of the rated current. IC is also going to be really, really small because the hysteresis loss and eddy current losses will not be much in a transformer. The efficiency is generally very high. We already said about this. So the no load current, what is drawn by the transformer is the summation of the core loss component of current and magnetizing current. And this is going to be really, really small. So if I call this current as I2 dash, which is also incidentally the load current, I2 dash plus I naught, both of them being phasors, these two added together will give me what is I1, which is the current drawn from the primary side. And I naught is generally less than 5% of the rated current, that is I1 rated. So we can say 95% or even more makes up for I2 dash. And that is the reason why we can afford to neglect this parallel component or the current that is flowing through this RC and XM. We can neglect it. So on the whole, if I try to look at the transformer without the parallel parameters, we are going to have R1 and we are going to have R2 dash, and we will have X1 here and X2 dash here. So these are the series parameters that come directly, which are responsible for the internal voltage drop within the transformer. And we are going to have V1 applied here. And what is coming across the load? Let us say this is the load. So this is going to be V2 dash. So V1 minus V2 dash, that is actually the voltage drop within the transformer. Now, this voltage drop, if I may call this as VD, now VD divided by whatever is V1 rated or V2 rated. What we mean by V1 rated or V2 dash rated is if we are saying it is 220 divided by 110 volts transformer, we expect the voltage to be staying put at 220 volts. If I look at it from the primary side, and I want the voltage to be staying put at 110 volts if I'm looking at it from the secondary side. So if I transform the secondary side voltage to the primary side, it should still be 220 volts, which should be constant. So this, in this particular case, we should write this as VD, voltage drop, which is visualized from the primary side. So VD visualized from the primary side, from primary side. divided by V1 rated. In this particular case, V1 rated is 220 volts. So this is going to give me what is the regulation. So the regulation, voltage regulation of the transformer. Now, if I want to express it as percentage, that is how much percentage of V1 rated is dropped as VD. In that case, I have to write this as percentage voltage regulation. This percentage voltage regulation is going to be VD divided by V1 rated multiplied by 100. So this is going to be percentage voltage regulation. So the lower the voltage regulation, the more constant the voltage is going to remain as far as the output side is concerned for the transformer, irrespective of the variation in the load current. The load current could be very high, that is rated current, or it could be very, very small. Irrespective of the current drawn by the transformer, whatever be the current drawn by the transformer, I want the output voltage to remain as a constant. If that has to happen, that means I should have these resistances to be very, very small and the reactances to be very, very small. Only then we are going to have the drop to be very, very small, in which case the voltage regulation will also be small. If the voltage regulation is small, that means we are going to say that the performance of the transformer is really good. Now, what we will do is this R1 and R2 dash put together, we will write that as R equivalent. Similarly, X1 plus X2 dash put together, we will write that as X equivalent. So on the whole, we should be able to draw the transformer equivalent circuit somewhat like this. This is R equivalent and this is X equivalent. And I'm applying V1 here. And what comes out here is V2 dash. And R equivalent is consisting of both the primary and secondary winding resistances, but they are translated onto the primary side. X equivalent consists of the leakage reactances of both the primary and secondary winding, but they are all translated into the primary side. So from here, let us now try to draw the phasor diagram so that we would be able to calculate the regulation properly. Okay. If you may recall, we had said that the overall equivalent circuit of the transformer consists of an R equivalent, which is actually R1 plus R2 dash. Similarly, X equivalent, which is X1 plus X2 dash. X1 being the leakage reactance of the primary winding, X2 dash is the leakage reactance of the secondary winding as seen from the primary side. Similarly, R1 is the resistance of the primary winding, R2 dash is the resistance of the secondary winding as visualized from the primary side. And this V1 is the voltage that is being applied here, and V2 dash is the voltage which is appearing across the load. This is the output voltage. Of course, we have neglected. So RC and XM are neglected here. When we are calculating the voltage regulation, we are neglecting these two. Okay. So let me start by explaining this phasor diagram, what I have drawn. So let us say this V2 dash, what we have got here, this is the voltage that is coming across the load. And let's say there is a lagging power factor current, which is actually I2 dash. So I'm going to call this as the load power factor, phi L. So this is going to be the load power factor, which is phi L. Now, if I extend this particular V2 dash further, so I can just draw it like this with the dotted line. And along with that, I'm going to exactly draw I2 dash times R2 dash, which is going to be in phase with this I2 dash. These two things are going to be in phase with each other. So this is representing the drop in the resistance. I should not even say R2 dash. I should rather say R equivalent. I should write this as R equivalent. So I should not write this as R2 dash. I am rather writing this as I2 dash R equivalent. Similarly, I should write here perpendicular to this whatever I have drawn. That is actually representing the reactance drop, which is I2 dash X equivalent times J. So this is the reactance drop in this particular reactance, and this is the resistance drop which takes place in this resistance. When you add these two, what I get is in the black color, what I have shown, which is I2 dash times Z equivalent. So what I have written here is I2 dash times Z equivalent. So that is the total drop that is taking place in these two elements put together. So I should be able to say V2 dash plus I2 dash, whatever be the phase angle of I2 dash, I have to take that also into consideration. So I'm writing this as a vector multiplied by R equivalent plus J X equivalent. So I can write this as V2 dash plus I2 dash vector multiplied by Z equivalent. Not only the magnitude along with the phase angle. Phase angle, let me call this as phi equivalent. Okay, so this is going to be the phase angle of Z equivalent. So this is going to be what is the voltage V1. And for calculating regulation, I can write V1 minus V2 dash is the total voltage drop in the transformer. Drop within the transformer. So if this is the total voltage drop within the transformer, which I may call as VD or something like that, voltage drop VD, I should say VD divided by whatever is V1 value, this multiplied by 100. That is going to be percentage voltage regulation. That is going to be the percentage voltage regulation. So I should be able to write here, if I look at this as I2 dash Z equivalent, then when I add V2 dash and I2 dash Z equivalent, this green color line what I have drawn, that vector represents what is the applied voltage. Okay. Now I can draw a perpendicular, I can drop a perpendicular from here to V2 dash. So let me try to drop a perpendicular like this. So what I have drawn is, if let's say this is V2 dash and I have got V1 like this, what I have drawn is to drop a perpendicular like this. That's what I have done. Okay, so this is 90 degrees. Okay, now if I look at this particular angle between V2 and I2, we call this angle as phi L. What we called this angle was phi L. And if I try to look at what is the angle here, this is the impedance angle of the transformer impedance itself. So that is going to be phi equivalent. So if I try to look at what is the angle here, that is, if I try to look at only this angle here, this angle will be phi equivalent minus phi load. This is the angle I'm going to get as far as this is concerned. This is the angle, which is made by I2 dash Z equivalent with V2 dash. So that is going to be phi equivalent minus phi L. So now I can calculate V1, which is the hypotenuse. Let me probably write the name of this triangle. So let's say this is O, and let me call this point as P, and let me call this point as some Q. So I should be able to write OP square equal to OQ square plus PQ square, right? So in which case I should be able to write this is V1 square. OQ square actually I can write as two components. One is V2 dash plus I can write this is I2 dash Z equivalent with the angle which is phi equivalent minus phi L. So this is the adjacent side of this triangle, if I may call this as R. So I should say RQ is the adjacent side of this right angle triangle. So I should be able to write this as I2 dash Z equivalent multiplied by cos of phi equivalent minus phi L. This whole thing whole square corresponds to OQ square. That is what it is, right? And PQ square is going to be the opposite side of the same triangle PRQ. So I should say that is I2 dash Z equivalent multiplied by sine of phi equivalent minus phi L. Okay. Generally, the drop within the transformer is going to be so small. Even the angle between these two will be generally very small. So also will be the case with this. So that is the reason why you are going to see that this distance, this is going to be really, really small. So we are going to neglect this. This is an approximation, but practically this sine of phi equivalent minus phi L is going to be really small. So we are essentially neglecting it. So we should be able to write this as V1 square equal to V1 square is equal to V2 dash plus I2 dash Z equivalent cos of phi equivalent minus phi L the whole square. So I can simply remove the square on either side. So I should be able to write this as V1 minus V2 dash will be equal to I2 dash Z equivalent multiplied by cos of phi equivalent minus phi L, which can be written as cos phi equivalent cos phi L plus sine phi equivalent sine phi L. So I can write this as I2 dash multiplied by Z equivalent cos phi equivalent, which is actually R equivalent. So R equivalent cos phi L plus X equivalent sine phi L, right? Multiplied by I2 dash. That is going to be the voltage drop. This is going to be the voltage drop, what is seen. So this divided by V1 should be able to give me the regulation. So if I multiply that by 100, I'll get percentage regulation. RC is the core loss component of resistance. So when you draw the equivalent circuit, you are going to say this is R1, this is X1, and you normally have RC and XM like this, right? This is what we drew as the equivalent circuit initially. And then I drew R2 dash and X2 dash. Right. And then we said that V1 is applied here. And this is V2 dash with ZL dash being connected here. So this RC and XM represent the no load parameters. When there is hardly any load connected on the secondary side, the current drawn by the transformer is generally known as the no load current. So this is going to be I0 and this is going to be IC and this is going to be IM. So what is flowing through which component this IC is flowing, that is generally known as RC, which is the fictitious component which is corresponding to the iron loss that is taking place in the transformer. No load current we are neglecting. Because no load current is going to be less than 5% of full load current or rated current. So we are going to neglect it, and neglecting that practically does not affect when you try to assess the performance of the transformer. So that's why I said engineering is all about approximation. The approximation you make does not affect the realistic value what you get experimentally. As long as that is true, it's fine. So reasonable assumptions are fine. And how do you verify whether it is reasonable? By conducting an experiment and then checking whether you are getting the values you estimated to be the actual experimental values as well. If at all there is a difference, the difference is negligibly small. Okay, so let me maybe summarize what we did in transformer. So summary, if I try to write, we started with the basic principle of operation of transformer. So we said electromagnetic induction, primary, secondary, and then core, and then ampere turn balance, all those things we talked about. I also talked a little bit about construction because I said it will be made up of laminations and then iron core or ferromagnetic core, and around which we are going to have windings, primary and secondary. So we talked about that first. Then after that, we slowly got into the real ideal versus real transformer. Ideal transformer, we said literally will have infinite permeability of the core, whereas real transformer will require certain amount of current for establishing the flux. Then we talked about leakage in this. And we also talked about leakage flux, how that can be reduced. So reducing leakage, that also we talked about a few methods. Okay, and after that, we came into the equivalent circuit of the transformer. So we derived the equivalent circuit completely. And we said how all the parameters for the secondary side can be transferred on to the primary side by using, for example, R2 dash equal to R2 multiplied by N1 divided by N2 the whole square. So this is the secondary resistance transferred to the primary side. So this we said already. Then we talked about what are the performance parameters of the transformer. But before that, we said determining the equivalent circuit parameters by OC and SC test, open circuit and short circuit test. So this we talked briefly, and after that, we talked about the two performance parameters, namely efficiency and voltage regulation. And in efficiency, we specifically derived what is the maximum efficiency condition. And we said that from that, how you could be in a position to determine what are the copper losses, what are the core losses at rated condition or at any other condition, and then how you can estimate the efficiency of the transformer at any other load and at any other power factor. Voltage regulation, we derived the expression which is I2 dash multiplied by R equivalent, or IL dash, you can say the load current that is visualized from the primary side. So IL dash multiplied by R equivalent cos phi L plus X equivalent sin phi L. So this is the voltage drop. This has to be divided by V1 rated. If I am looking at it from the primary point of view, and I have to multiply this by 100 if I want percentage voltage regulation. And we said very clearly that sin phi L will be positive if it is a lagging load, for lagging power factor, and it is going to be negative for leading power factor. Leading power factor. Okay. So this is what we said with respect to transformer. I thought before I conclude everything for this course, I will give you a kind of qualitative explanation, little bit about first generators and motors, and also some kind of sensors and transducer. Okay, so I'll just give some amount of explanation about these things, and then with that we'll conclude the course. Okay, so as far as generators go, I think I already introduced a little bit for you as to how the generators work. This was when we talked about single phase as well as three phase. So one phase and three phase AC circuits, when we talked about, I mentioned to you as to how the generators work. So let me reiterate that a little bit. So if I look at an AC generator, the case is going to be somewhat like this. I'm going to have one winding like this. One may carry current, let us say, out of the board. The other may carry the current into the board. So I may have, this is the cross section I'm showing. And I'm going to have basically, I'm just showing only one conductor on the positive side and one conductor on the negative side. And if I say that I'm going to have a magnet, which is somewhat like this, and I'm going to have this as North Pole and this as South Pole, and I'm going to have this in the center, which is actually connected to a shaft. So this is actually going as the shaft. So in generator, what is done is the mechanical energy that is supplied to the generator is going to be converted into electrical energy or electricity. This is what happens in a generator, and the via media, it is actually converted into electricity through a magnetic via media. So you are going to have a magnetic field which is sitting in between, which is going to work like a catalyst, and it is going to facilitate the conversion of mechanical energy into electricity. So the mechanical energy what is given to a member called rotor. So you are going to have two members in any generator. The first member is going to be stator. The next member is going to be rotor. So the stator is stationary. It is not going to rotate. It is going to just stand still. And the rotor is the one which is moving. So this is going to rotate. Okay. So in this particular case, I have shown as though the outer circle what I have. So I'm going to have actually slots carved like this. So it is a hollow cylinder. What I'm going to see as the stator is going to consist of hollow cylinder like this. And in the hollow cylinder, in the inner periphery, there will be slots that are carved. So once the slots are carved, you are going to put the conductor into that. So the conductor is going to go like this into the machine, and then it may turn around like this and then come out through this portion. So this is how the conductors are going to be placed within the machine, the stator. So the conductor is placed somewhat like this, and you are going to see that because it is stator, these conductors are stationary. They are remaining stationary. Under such a situation, now if I have a rotor which is consisting of a magnet, the magnet can be a normal permanent magnet, what you see. Normally the magnets that are available for, for whatever play purposes, or you might have seen that the refrigerator magnets, what you have, sometimes you just put some of the papers and everything using those magnets and then stick it onto the refrigerator. So those kinds of magnet, the permanent magnet, can be a part of this rotor. So this is a magnet. So this magnet is actually attached to the rotor along with the shaft. So this rotor shaft is going to be coupled to, let us say, your hydro turbine or your steam turbine, which is there in the power station. So it is going to be rotating this magnet at a particular velocity as decided by whatever is your prime mover speed. The prime mover is either a hydro turbine or steam turbine. So now this magnet rotates. Because the magnet is rotating, if I look at this conductor, let me call this conductor as A and this conductor as A dash. So I'm going to see that A probably faces north pole at some point, south pole at some point, and no pole at all at some point. So both A and A dash are going to see a rate of change of flux. Both of them are going to see a rate of change of flux. If both of them are seeing a rate of change of flux, then what is going to happen is Faraday's law is going to come into play here. So we are going to have d phi divided by dt. That is happening. The rate of change of flux is happening here. So d phi by dt is going to be proportional to the EMF induced. So if I call North Pole as carrying some positive flux, obviously South Pole will carry the negative flux, or both of them are going to have opposite effects. So I should say whenever A is facing North Pole, A dash is facing South Pole. So if A is getting a positive induced EMF, A dash will get a negative induced EMF and vice versa. So both of them are going to be additive. So if I try to look at the induced EMF, if I say this is positive induced EMF here, this is going to have a negative induced EMF here, which means I'm going to have this somewhat like this. This is how it is going to be. So it is like connecting two batteries in series. So they are going to be in series addition. That is the reason why I'm going to get twice the voltage generated in one conductor as the resultant voltage, what I see across A and A dash together. So what we are going to see is if I bring out this particular wire outside and connect it to a load, maybe a resistance or something, and if I try to look at how much is the voltage across this. So let us say this is minus and this is plus, and try to measure the voltage across this. It will be twice the voltage of what is induced in each of the conductors. So the basic principle of operation of a generator in general is that we are going to move a conductor in a magnetic field. Either we have to do this, the magnetic field can be a constant magnetic field, or the other way around is move a magnet in the vicinity of a stationary conductor. Either way is fine. So the moment we do this and we provide a closed path for the conductor to carry current, then it is going to induce an EMF first of all in the current and in the conductor, and the conductor is going to pass current through this resistance or any other load that is connected. Okay, so this is the basic principle of operation of a generator. So as I told you, the induced EMF what we see in a generator, this is the EMF that is induced. Let us say that is going to be some voltage V. So that is going to be proportional to d phi by dt. So how fast the rate of change of flux is happening, that depends upon two parameters. One is the strength of the magnetic field itself. And the second is how fast the magnet is being rotated or moved. So in general, the speed of rotation is also going to determine how quickly your rate of change of flux is happening. So I should say V is proportional to flux multiplied by speed. Both of them are going to play a vital role in terms of determining what is the value of induced EMF. So this particular concept of induced EMF being dependent upon speed in a generator can be used for sensing speed. So in most of the apparatus which are used for sensing the speed, we invariably will be using the principle of generator. So whenever we want to sense speed, we will be using principle of generator. Because we say that in a generator, we say that the speed is proportional to the induced EMF when flux is a constant. We are not going to change the magnetic field or magnetic flux. So what we tend to do is we use a permanent magnet kind of generator. So we just have a magnet which is something like this, North Pole and South Pole, and we are going to have basically a shaft whose speed I want to sense. So this is the shaft which is attached here, and I'm going to have the shaft going like this, and I want to know how much is this rotational speed of this shaft. What is the speed I want to sense? So if I have a generator which is basically having the conductors inserted here, maybe I'm going to have this as the slots. So I can have multiple number of conductors probably. So let me just show one conductor on one side and another conductor on the other side, which is just turning around and coming back. Okay, so this is the complete stator structure. What I have shown, this is the stator structure. So I'm going to have, let us say, one conductor here and exactly opposite to that another conductor here. So I can actually look at what is the kind of voltage that is coming across this. I can put a voltmeter here to measure the exact value of voltage. So this voltage, if I am able to measure, that will give me an estimate of speed, because I know what is the magnetic strength, magnetic field strength I have, because this magnet's original flux value and everything I will know. So I should be able to say if the voltage induced is 10 volts and if the RPM at which it is rotating is 1000 RPM. For example, if I am having an induced voltage of only 5 volts, I know for sure that maybe the machine is rotating only at 500 RPM. On the other hand, if I'm going to have 15 volts, I can say the machine is rotating or this shaft is rotating at 1500 RPM. So by measuring the voltage and calibrating the entire apparatus properly. What do you mean by calibrating? I should know already by some means that my particular shaft is rotating at 1000 RPM. And at that point, I'm getting 10 volts. I will just cross verify this. Again, I will rotate it at 500 RPM and I will see whether I'm getting 5 volts. So I know now that whatever is the voltage that is induced, I should multiply that by 100 to get the speed in RPM, revolutions per minute. So the generator action itself can be used as a speed sensing mechanism. And we normally call this kind of generator, which is used for sensing the speed and which is meant, which is rather equipped with the permanent magnet within itself, this we generally call as tacho generator. Tacho generators are very commonly used for speed sensing in many of the systems. For example, if it is like a printing press, or if it is like a steel rolling mill, or if it is like a cement mill, you know, or even in an electric vehicle, I will be able to really get what is the speed by making use of a tacho generator. So the tacho generators are very, very commonly used for speed sensing. Exactly. See, if you know really the magnetic field strength a priori, then you will be able to derive this theoretically. It is not a big deal. But how much is the error involved? What is the kind of, margin you have to give in terms of the error that can crop up while measuring the speed? That you can do only experimentally. So you will normally calibrate an instrument to know how accurate the measurement is and what kind of error margins you have to give in this particular apparatus, the speed measuring apparatus. Okay, got it?
Yes.
Yeah. Any other questions?
Yes.
Any other questions? So along with this, let me try to talk a little bit about current sensing and voltage sensing. After that, I'll go over to the linear actuator and motor. So current sensing and voltage sensing. How this is done generally. I'm talking about sensing. I'm not talking about measurement. There is a big difference between the two. The measurement is basically done by a human being. You are going to measure something, you know how to read it, and you are going to record it somewhere. Whereas if I am sensing it, in all probability, I'll be sending it to another mechanism which is actually regulating it. For example, I'm sure all of you know that in air conditioner you set a temperature and you want the room to be cool to that particular temperature. That kind of a system is called closed loop system, closed loop control system. So in a closed loop control system, what you tend to do is, for example, let me talk about an air conditioning system. So what you would do is to set a particular temperature. So I'm going to say, this is the reference temperature I want to reach. And you are going to compare that with what is the actual temperature of the room. So this is the actual temperature that you are going to sense from the room. So this is sensing. You are going to sense the actual temperature using a thermostat or whatever. Now, whatever is the error, this is going to tell us whether I should cool the room further, or right now whatever is done, that is sufficient. So this is going to give me a signal. So what is coming out is an error signal. So this is going to be the error signal what is coming out. So this error signal will be processed, whether I have to cool it much faster, whether I have to just stop it, whether I have to cool it slowly, because the difference is very, very low. Now this processed signal will be given to the compressor. The air conditioning system will have a compressor. The compressor will continuously be turned on and turned off respectively, because it will compress the coolant and it will allow it to expand. Okay, when it is expanding, it will cool the surrounding air also. That's what it is going to do. So the compressor, whether it has to work or not, will be decided by the difference between the reference temperature and actual temperature. And I am going to actually, so this is the compressor's coolant mechanism is going to give the output actually to the cooling system. Now the cooling system is actually blowing out the cold air into the room. So this is coming into the room. Okay. Now the room's temperature I have to measure. So I have to have something like a temperature sensor here. So the temperature sensor does not measure and tell you this is what is the temperature. That is a display unit what you have on the air conditioning unit, but that is not the point. The temperature sensor has to send a signal in the form of some electrical signal or some other signal to the control unit so that the reference temperature and the actual temperature will be comparable. These two will be compared and it will be processed further as the error. Okay, so generally, the sensing mechanisms will require an electrical signal from your transducer or sensor so that it can be processed further. Whereas the measurement unit will show in the form of a display what is the temperature or what is the pressure, what is the voltage, what is the current, so that the human beings who are standing there doing the experiment will be able to read it. So there is a big difference between the sensor, which is really not read by a human being, it is actually going into another mechanism. So how to sense the voltage or current? We look at it. The voltage and current sensing can be done with the help of a transformer. Then you may have a simple rectifier unit. And then directly this particular voltage or current will be, the information will be disseminated to the control unit. So the transformer essentially works only for either stepping down the current, because you may be measuring thousands of amperes of current, or you may be stepping down the voltage, because you may be measuring thousands of kilovolts. That is possible. So either you have to step down the current or step down the voltage before you really feed it to the control unit. Please remember, most of the control units are electronic circuits, and electronic circuits only work at anywhere between 0 to about 15 volts, and similarly only of the order of milliampere. So it is extremely important to step down the current to milliampere range or step down the voltage to 0 to 15 volts range. Otherwise your electronic circuits will conk out. They will not work properly. Okay. So invariably voltage or current sensing is generally done by transformer, by making use of transformer. Okay. So we had been talking about voltage and current sensing, and we said that for both voltage sensing and current sensing, we will require basically a transformer for stepping down. So we will require a transformer for stepping down either the voltage or current before it is actually measured or sensed. So in voltage sensing case, it has to be a step down transformer, which means if I want to measure kilovolts, from that, the voltage has to be stepped down to a few volts. So in that case, I'm going to have something like 1000:1 as the number of turns. The same way, if I want to sense the current, it should be something like a step-up transformer, because when the voltage is stepped down, the current is stepped up and vice versa. So I am looking at maybe from amperes, I want to look at only milliamperes so that it can be sensed by an electronic circuit. So I'll have to have 1:1000, something like that, as the turns ratio of the transformer, which is being used for sensing the current. So in either case, it can be done only for alternating. That is, I can use a transformer only for sensing alternating current or alternating voltage. So I can use a transformer only for sensing an alternating current or alternating voltage. Whereas if it is DC, it is not going to be easy for me to use, it cannot be is not possible for me to use transformer. So I have to find definitely some other method for sensing the current, DC current or DC voltage. I'm not going to expand upon this much in this particular course, but we will continue with sensing in the next class as well.